Okay, so now that we've had a look at the electromagnetic spectrum, we can go back to comparing some of the wave properties and particle-like properties of light. Looking at some of the wave properties of light. So these are properties that you would not expect to be exhibited by matter. That is, things that physically exist, objects, particles, should not be exhibiting these properties. And things that are made up of waves should be exhibiting these properties. So one would be interference and diffraction. And this has to do that waves can interact in ways that either reinforce each other or counteract each other, depending on how the waves are synced up with each other in space. When they reinforce each other, that's known as constructive interference. And that would be a case where, for example, this would be in phase interference. So in other words, you have a wave that's sort of synced up like this, and you have another wave that's synced up exactly like that. And they can combine with each other and make it like there's one bigger wave. Okay, also, they can interact in ways that counteract each other. And that's known as destructive interference. And that would be out of phase interference. And that can take the form of partial or total. So total out of phase interference would be kind of a situation like this, where the peaks of one wave line up with the troughs of another. And the effect of that would be basically they cancel each other out totally. There's also partial destructive interference, where the waves are not in phase, but they're not totally out of phase either. And so you might have one wave that looks kind of like that, and one wave that's off a little bit, and allowing for my feeble artistry, you would end up with them combining into, it's still a wave, but they're smaller because they partly interfere. They're kind of off kilter relative to each other. I'm trying to make it look like they're a little more out of phase than they are than they were originally. Okay, so that would be like a partial out of phase or destructive interference. Another property of waves is diffraction. That's a wave property. You would not expect matter to be diffracted. When a wave encounters an obstacle or a slit of a size that's about the same as the wavelength of the wave, then the wave will bend or diffract around it. And a good example of that is shown at the bottom of page 283. See, 283. There we are. This diagram here. When you have a single slit that's about as wide as the wavelength of the waves are, then what you get is the waves sort of bending around that slit like this. And that's a diffraction pattern. Whereas if you had a beam made up of particles instead, this is what would happen. Some of the particles would bounce off if they hit the basically hit the wall where there's no slit. The particles that hit the area where there is a slit would go right through, and there would be no bending, no diffraction pattern, anything like that. Okay, so clearly, since light is diffracted, then we can say that light must be made up of waves. Also, there's the double slit experiment that's on the next page in the textbook. And with that, we see the effect of light encountering two slits that are a distance apart that's about the same as the wavelength of the light. The waves basically will interfere with each other. And in some areas, they will interfere constructively. And in other areas, they will interfere destructively. And that's why you get this light-dark pattern. The light spots are where the light is interfering constructively, and the dark spots are the areas where it's interfering destructively. And so destructive interference basically cancels, if it's total destructive interference, then it basically cancels out the waves and you get nothing but a straight line. If the waves are in sync with each other totally, then they enhance each other, like this. And again, those are things that you would expect waves to do, not things that you would expect particles to do. So again, if the light encounters two slits separated by a distance that's about the same as the wavelength of the waves, then what you get is an interference pattern. With alternating areas of light and dark corresponding to constructive and destructive interference. Okay, so light does that too. So that's another sort of piece of evidence in favor of light being a wave. On the other hand, as I said, it kind of spoiled the surprise up front. Light also has some properties that you would expect to see from particles and not waves. So the particle nature of light, one actually that the book doesn't go into, but I'll mention it up front, and then we'll go into the ones that the book does go into detail about. Is that light is actually capable of exerting pressure on objects that the light falls on. Pressure is defined as the amount of force that's exerted per unit of area. Only particles can exert force. Waves don't. I mean, waves that are not made up of particles. Mechanical waves, like ocean waves or sound waves, they can exert pressure, but not waves that are not, the types of waves that are not made up of particles couldn't do that. And if you think of, say, the pressure of the air around you, it's caused by the fact that the air is made up of little particles like oxygen and nitrogen, and those particles are zipping around at a high rate of speed, and eventually they hit something. And if you define a certain area of the wall, like 1 square inch, those particles of the air will be hitting that 1 square inch with a certain amount of force. And so, say, pounds per square inch would be a unit of pressure. But like I said, you have to have some physical being in order to exert that force. So the fact that light exerts pressure, it's a very small pressure. You need very sensitive instruments to measure it, but it does exist. And so light must have particles associated with it. Another thing that leads us in the direction of light being made up of particles would be the photoelectric effect. The photoelectric effect is seen when you shine light on certain substances. And those substances then release electrons. And a good example of this, of course, is solar cells. Solar cells that you might use for solar energy in a house, or even the solar cell in a calculator would be a good example of the photoelectric effect. Sorry. Okay, I'm done. This was originally thought to be due to transfer of energy from the light waves. Okay, so it was originally thought to be due to a transfer of energy. But when people started doing experiments with it, sorry, they found that changes in wavelengths or the amplitude of the light have very little or no effect. And what they found, in fact, was that there's something that's called a threshold frequency. And that is basically the lowest frequency that's capable of causing the substance to emit electrons. And if the photoelectric effect had been caused by wave properties of light, you wouldn't expect that to be the case. Okay, you would expect that basically there'd be one frequency that would release electrons, and if you increased the frequency, thereby increasing the energy, you should increase the number of electrons that are being released. But that actually doesn't work that way. Any frequency above the threshold frequency will cause emission of electrons, and it'll basically cause the emission of the same number of electrons at the same rate. It was the photoelectric effect that won Albert Einstein his first Nobel Prize. And he proposed in 1905 that light energy comes in packets. These packets are really small, but they are discrete, meaning they're separate. These packets are known as quanta, or quantum in the singular. And they are particles. And we call them photons. And so a photon is just the particle that's associated with light, or rather the particle properties that are associated with light. It's really hard even to describe it because we're down at the level now where things get really weird. Because, for instance, I mean, if you think of photons as being the particle that's associated with light, okay, fair enough. There's a particle associated with light. If it's a particle, what's its mass? Oh, it doesn't have a mass. It's like, what? Mass is a measurement of the amount of matter in an object. An object, better known, is a particle. In order to be a particle, something has to physically exist. And in order to physically exist, that substance has to have mass and volume. But yet the photon doesn't have mass. So, yeah, we're getting pretty weird now. The energy of each photon of light is given by an equation that involves either the wavelength or the frequency. And that's E equals h nu, or E equals hc over lambda. And you might be wondering what that h is. H is Planck's constant. It's a proportionality constant between the other terms that are involved in the equation. And Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And that value, it's in all kinds of tables of constants and things that you can look up. And c, of course, is the speed of light, which is 3 times 10 to the 8th meters per second in in air or vacuum. And so now we can find the energy of each photon of a given light just based on the wavelength or the frequency. And because light consists of photons, that means that the amount of energy that you can get from light comes in these little packets because of there's a certain amount of energy that each photon has. And for that particular wavelength or frequency of electromagnetic radiation, that is the smallest amount of energy that can ever exist for that particular kind of electromagnetic radiation. So the energy of light from electromagnetic radiation is not infinitely variable. There's a certain minimum amount that you can have. And so, in other words, the energy of one photon of light for a given wavelength and frequency is the minimum amount of light that's, or the minimum amount of energy that's possible for that particular wavelength and frequency. You could never have a change in energy for that particular wavelength and frequency that would be smaller than the energy of one photon. So that's what we mean by when we say that it's not continuously variable or not infinitely variable. So for instance, say a 100-watt light bulb gives off light with a wavelength of 525 nanometers. How many photons per second would be given off? This may seem at first like kind of an off-the-wall question. How on earth are you going to do that? Well, what you need to remember is a watt is a unit of power, and power is energy per unit of time. In this case, a watt is equal to a joule per second. So a 100-watt light bulb is giving off 100 joules of energy per second for every 1 second. So now that we realize that, we're going to find the energy of each photon of the light. So the energy of each photon, let's see, we have the wavelength. That's hc over lambda. So h is 6.626 times 10 to the minus 34 joule seconds times speed of light, 3 times 10 to the 8th meters per second, all over the wavelength. The wavelength was given in units of nanometers. A nanometer is just 10 to the minus 9 meters. So rather than going through the whole process of trying to convert this into meters, we could just actually substitute 10 to the minus 9 for nano. Because again, a number does not have to be in proper decimal or scientific notation form unless it's the final answer to a question. And this is not the final answer to the question. This is one of the numbers that's going into the answer. And in fact, the answer from this is not even going to be the final answer. So you can use it as 525 times 10 to the minus 9 meters. That's the easiest way to write it. And it's perfectly true. It's just not proper scientific notation. So if you multiply that out and divide, remember to use parentheses around the number on the bottom, you get 3.79 times 10 to the minus 19 joules per photon. Okay, so that is the energy per photon. If we then basically take the fact that there is are 100 joules being okay. What was the question again? How many photons per second? Okay. We've got joules per second, and we've got joules per photon here. So if we arrange it so that we have joules per second times photons per joule, which would just be this number upside down, joules cancel and we have photons per second. So that's what we're going to do. We take the 100 joules per second, and 3.79 times 10 to the minus 19 joules per photon just means there's one photon for every 3.79 times 10 to the minus 19 joules. Okay, so that's what I meant by using this number upside down. Joules cancel. We end up with photons per second. And that is 2.64 times 10 to the 20th photons per second. And so there you go. We could look at another example along these lines. The energy required to dislodge an electron from sodium via the photoelectron effect. Okay, so in other words, we're saying what wavelength of light has enough energy per photon to do this? Okay, and 275 kilojoules per mole. Huh, that part of the question I kind of forgot to write in there. Okay, so the energy required is 275 kilojoules per mole. In other words, that's 275,000 joules per mole. And so $275,000 joules per mole of photons. And if we want to know individual numbers, of course, the number of items in a mole is Avogadro's number. 1 mole of anything is 6.022 times 10 to the 23rd photons. And now you notice moles cancel and you have joules per photon. And we know if we want wavelength, we can use the equation E equals hc over lambda, but we're going to have to rearrange it to find lambda. Lambda is hc over E, because when you're looking for something that's on the bottom of a fraction, you can exchange it with whatever is on the other side of the equal sign. So lambda is hc over E. H is the constant, 6.626 times 10 to the minus 34 JS. C is the speed of light, 3 times 10 to the 8th meters per second. And energy we just found above, 4.57 times 10 to the minus 19 joules per photon. I'm going to leave it as just joules. because the word photon is often left out. Okay, if you work all of this out, we get 4.35 times 10 to the minus 7 meters, or 435 times 10 to the minus 9 meters. And the reason I said that is because, let's see, I don't think the question actually specified units, but this is visible light, and we usually report the wavelength of visible light in nanometers. So 4.35 times 10 to the minus 7 meters would be the same as 435 nanometers. But if units are not specified in the question, then you could use it, leave it in either one of these. You wouldn't want to use that as the final answer because that's not proper scientific notation and not a proper decimal form either. But either of these would be acceptable. Okay, so that brings us to about 30 minutes. So I'm going to stop here for the next segment.